Hi, in this video we would discuss about the HOGWILD algorithm, which is a lock-free approach to parallelizing stochastic gradient descent. Before starting, I would like to introduce myself. My name is Himanshu Sekhar and I am currently pursuing MTech in data science from IIT Guwahati. So at first we would look at what is the motivation behind parallelizing the SGD. So the first question arises is why to parallelize SGD. So stochastic gradient descent SGD has proven to be well suited to data intensive machine learning tasks. The emergence of inexpensive multi-core processors has motivated researchers to develop several clever parallelization schemes for SGD, but SGD is difficult to parallelize. As many large data sets are currently pre-processed in a MapReduce like parallel processing framework, much of the recent work on parallel SGD has focused naturally on MapReduce implementation. So the problem with parallelizing and the proposed solution is discussed in this slide. So several researchers have recently proposed schemes to parallelize SGD, but all require performance destroying memory locking and synchronization. The aim is to show that SGD can be implemented without any locking. The proposed solution, which eliminates the overhead associated with locking, is to run SGD in parallel without locks, and the strategy is called HOGWILD. HOGWILD allows processors access to shared memory with possibility of overwriting each other's work. It is noted that when the associated optimization problem is sparse, meaning most gradient updates only modify small parts of the decision variable and the memory overrides are rare, then HOGWILD achieves a nearly optimal rate of convergence. It is observed experimentally that HOGWILD outperforms alternative schemes that use locking by an order of magnitude. There is a near linear speed up with the number of processors on commonly occurring sparse learning problems, and which is great. So now we would discuss about sparse separable cost functions. So the key observation is that the natural cost functions associated with many machine learning problems of interest are sparse. Some of the examples include sparse SVM, matrix completion, graph cuts. So what is the HOGWILD algorithm? So before talking about the HOGWILD algorithm, we will discuss about some assumptions which we make. The first assumption is a shared memory model with P processors. Each processor can read X and can contribute an update vector to X. The vector X is stored in a shared memory, and we assume that the component wise addition operation is atomic, that is XV. The update of XV from XV plus A can be performed atomically by any processor for a scalar A and V lying between 1 to n. Note, this operation does not require a separate locking structure on most modern hardwares. Such an operation is a single atomic instruction on GPUs and TSPs. So the algorithm is pretty simple. We just sample E uniformly at random from capital E, read a current state XE and evaluate GE of XE, where GE of XE denote the gradient or subgradient of the function FE multiplied by mod of E. So then for V belonging to E, we do the update where XV is updated to XV minus gamma GEV of XE. So basically the gamma is the step size, and which is a fixed size constant. So in the algorithm, each processor samples a term E belonging to E uniformly at random, computes the gradient of FE at XE, and then writes this update, which is xv, which is updated by xv minus gamma g ev of xe for each v belonging to E. So there are also some related works to HOGWILD. We'll discuss about that. So the work that is very much closely related to HOGWILD is round robin scheme. In this scheme, the processors are ordered, and each update the decision variable in order. When the time required to lock memory for the writing is dropped by the gradient computation time, this method results in a linear speedup, as the errors induced by the lag in the gradients are not too severe. However, we note that in many applications of interest in machine learning, gradient computation time is incredibly fast, and we now demonstrate that in a variety of applications, HOGWILD outperforms such a round robin approach by an order of magnitude. So this is a basic comparison of various clock times of HOGWILD and RR. So we can see that in the time required to compute for the computation for various approaches like SVM, MC, and graph cards for various data sets, the HOGWILD is basically beating the round robin approach. So some experiments have been performed for the comparison between these HOGWILD and round robin approach. So numerically, experiments have been performed on a variety of machine learning tasks and compared against a round robin approach to be as well as possible to prior art. RR, that is the round robin, was hand coded to be nearly identical to the HOGWILD approach. We also compare against a model which we call AIG, which can be seen as a middle ground between RR and HOGWILD. AIG runs a protocol identical to HOGWILD, except that it locks all the variables in E in before and after the for loop on line 4 of the algorithm. So when we see for different problems, the first is the graph cuts. So the problem was a standard image segmentation by graph cuts problem, popular in computer vision. Two-way cut of the abdomen data set was computed. This data set consists of a volumetric scan of a human abdomen, and the goal is to segment the images into organs. So the HOGWILD, we can see that the HOGWILD speeds up the cut problem by more than a factor of 4 with 10 threads, while RR is twice as slow as the serial version. We continue and we move on to the sparse SVM. So the sparse SVM implementation was tested on the Reuters RCV1 data set on the binary text classification task CCAT. Here we can see that the HOGWILD is able to achieve a factor of 3 speed up with while RR gets worse as more threads are added. So there one problem arises is that when what do we see if the gradients are slow? So with the DB live data set, the RR method does get a nearly linear speed up with the gradient computation when the gradient computation is slow. With some experiment, it is shown that if a gradient takes longer for more than 1 millisecond to compute, RR is on par with HOGWILD but not better. So the conclusion is the HOGWILD algorithm takes advantage of a sparsity in machine learning problem to enable near linear speedups on the variety of applications. HOGWILD is a way to parallelize HGD without any locking. Even if the gradients are slow, HOGWILD is either on par with RR or better than RR. So thank you.